अच्छा, ये स्क्रीन शेयर हो गई आप लोगों के साथ? स्क्रीन नजर आ रही है आप लोगों को? हम्म।
जी सर, आ रही है।
अच्छा, ठीक है। So this new lecture is about motion transformation, motion and power transformation. So we start out with the levers. I mean, you are familiar with levers. We're including it just for completion. So on the right hand side, if you see these three different types, so the common one is it's called the first order, yeah, lever, or lever of the first order, whichever way you say it. So the fulcrum is somewhere. I mean, you can't say it's in the middle, but it's between the load and the effort. Okay, so the load is on the one side and effort is on the other side. And if you know the effort, Fe is the effort, Fl is the load, and let's say these are the moment arm lengths A and B. So you can easily apply equilibrium. So A times Fl is the moment from the load side, and B times Fe is the moment from the effort side. And because they must balance out, so you just equate them, and this gives you the force ratio. Yeah? So you get the force ratio in that way. Um, you don't speak of velocity ratio here because you typically use lever for balancing, and it's a static equilibrium. So then you have a lever of the second order or second order lever. Their fulcrum is on one side and both the load and effort are on the other side. Now, what is special about B in comparison to C is that the load is between the fulcrum and the effort. Yeah, so load is in between. And in the third order lever of the third order, um, the effort is between fulcrum and the load. So I mean, you can write this equation for these two kinds as well. Okay, you just have to label them properly. So for example, in this case, this will be your, you can call this A and you can call this B. And because this force is upward and this load is downward, so these moments will balance out and you will see something very similar. Okay, I think I should have called this B and I should have called this A. Okay, if you want it to look similar to that. And similarly here, okay, you can call this B and you can call this A. And because these two forces are opposite, so the moments will balance out and so on. So pretty standard. Let's see if we can solve a few problems related to that. So we start with problem 20.9 from Bird and Ross, and you have a first order lever. So the load, so load is given to you. Okay, so which means that first you can sketch it. There is of the first kind. So fulcrum will be here, and the load is on this side. So let's say this load is 1.2 kilonewtons. Determine the effort. Now effort, because fulcrum is in between, so the effort will also be downward. So let's call this Fe, and the force ratio. So Fe is to be calculated and the force ratio is to be calculated. I've changed the notation from RF. We use this for force ratio, yeah, if you remember. That causes problems because sometimes we use R for radius. So I have changed the lecture notes and we will say FR for force ratio and VR for velocity ratio. Yeah, so that's something you need to remember. So now here the question is, we also need to calculate the force ratio and also the movement ratio. Yeah, we can calculate the movement ratio because you can think about small movement. Yeah, so when the distance between between the fulcrum and the load is 0.5 meter. Okay, so this is 0.5 meter, and the distance between the fulcrum and the effort is 1.5 meter. I don't know why I wrote it twice. Okay, so you just consider it once. Assume the lever is 100% efficient. Okay, so it just means there are no losses. So how do we go about it now? So the first thing you need to do is to write that balance equation. Yeah, and how do you do? It's actually 0.5 meters times 1.2 kilonewton. This will be the moment from the load side, and 1.5 meters times effort will be the moment on that side. You can solve this equation and you will get Fe. Okay, that's very straightforward. And force ratio will simply be FL over Fe. So now you know Fe and FL is given, so that's also straightforward. And the movement ratio, which is the velocity ratio. The velocity ratio can be calculated from the efficiency. We know the efficiency is 100%. Now efficiency, you know, is it was force ratio divided by velocity ratio. So if the efficiency is 1, this means that the velocity ratio must be equal to the force ratio. Yeah. So whatever answer you get here will be true for VR as well. So that was very easy. The second problem for levers is that this time you have a second order lever AB. So let's say you have a second order lever. Now second order lever means that the fulcrum will be on one side and the load will be, I forgot, and the second order load is in between. Yeah, so here you will have load FL and the effort has to be upward if you want to balance that. The fulcrum is point C, so let's call this point C, and okay, an effort of 60 Newton. Is it second order lever? Yeah, second order lever, yes. Okay. An effort of 60 Newton. So this effort is 60 Newtons at B. So let's call this B. Just moves a load at point D. This is point D. Okay. So which means that this point where there is no load and no effort, this must be A because he's calling the lever AB. Yeah. So AB means that it starts from A, it ends at B. At B you have the effort. At D you have the load. Okay, what else is given to us? When BD is 0.75. So this is 0.75 meters. And BC is 1.25 meters. Yeah. So calculate the load and force ratio. So how do we calculate the load? Again, you just write the balance. Yeah. So for the balance, you need this distance. Yeah. This distance is 1.25 minus 0.75. So what will be the difference? 0.5 5, yeah, 0.5 meter. So 0.5 meter times FL should equal, you see the moment is about the fulcrum. So 1.25 meters times 60 Newton, which is the effort. You solve this equation and you get F load. You get the load, sorry. And the force ratio is obvious. Yeah, you can do that yourself. It was also easy. Now that was quick. This topic is more challenging. So it's about gears, and gears are used to transmit motion. So there are different types of gears. So what you see on this side, yeah, these ones, they are called spur gears. Yeah, it's just a name. I don't know why they are called spur gears, but what is special about them is that these teeth are parallel. They are parallel to the shaft. So of course these gears will be connected to a shaft. So if the shaft is in this direction, these teeth are also in this direction. So that's why they are called spur gears. And this is typically what you see in diagrams. And then you can distinguish between external gears and internal gears. Yeah. So these are external gears. Yeah. Because they are on the outside of the um, body, which is used as gear. So and then there are internal gears, yeah, also called ring gears. So you see the object which you call gear has the teeth on its inside. Okay, so they are called internal gears. Yeah. Different applications. So, and of course one gear is never enough, yeah, because you want to transmit power. So there will always be more than one. So in the simplest case you will have two, or you can have more than two as well. So in that case the combination is called a gear set. Yeah. So what you see in these diagrams are actually gear sets. This is one gear set. This is another gear set. Yeah, and so on. So when you in gear sets you follow a certain terminology. So because you want this to transmit power, one side or one gear will be connected to the power source, like motor, yeah, or yourself. Maybe you are driving yourself. So that gear is the driving gear. It's actually called the driver, yeah, and it drives this one. So you can call this the follower. Yeah. In one terminology, you call it the driver. And remember, it's not necessarily small. I'm just giving it. In most cases, it is small, but it's not necessary. The driver is the gear which receives power from the outside, and it drives the other one. So this will be connected to the load. Yeah. And the driver will be connected to the effort. This is how you can remember it. Now, another terminology for driver is pinion. You will see it. So the driver is also called a pinion, and the follower is simply called a gear. When you use the terminology of pinion, then you simply refer to the follower as gear. So pinion gear. You also sometimes call it the output gear. Yeah, output gear and the input pinion. We don't need that. So okay. Now, of course, there is too much detail here, and if you want to analyze this, because one of the purpose of studying these things is to analyze motion and transmission, you can ignore a lot of detail, and you can simply have in mind equivalent cylinders, yeah, where you ignore these teeth and you just simply model them as cylinders, two cylinders, okay, and the shafts are actually shown in the middle. Now, when you model something as a cylinder, then two terminologies become important. One is called pitch radius and one is called pitch circle. So if I zoom this, basically, I have these teeth, yeah, and I can simply imagine a circle in between them. So the circle will neither be on one side nor on the other side, it will be somewhere in the middle. But because of the different shapes possible, it cannot be exactly in the middle. It has to be somewhere so that these two are equivalent. So what is important is the equivalence, okay? Remember, just like the center of mass, remember, center of mass is is a single particle which is equivalent to a whole rigid body. So here we want to have just two cylinders, and they should be equivalent to this gear set. And in that case, the radius of that cylinder is called the pitch radius, and the circle, which is equivalent to the gear, is the pitch circle. So I think you will get used to this terminology soon. It's just a simplification. So you can think of this as a way of simplifying things. Now, there is more detail, but I am not going to get into all the detail. When mechanical engineers, they design teeth, they use certain terminologies. So there is something called the diametral pitch. Now, what do you mean by that? So let's say you want to connect these two gears, okay? So in each gear, there is the number of teeth. So let's call this the number of teeth, the number of teeth. And then there is diameter, okay? So diameter. You can also call it twice the radius. Now this ratio tells you the number of teeth per unit diameter. Now this is called the diametral pitch, okay? You call this pitch. Now why is this important? If you connect two gears, it is for they can only run together without any problem if this ratio is the same for both, okay? You cannot have a different P here and a different P here. So P on this side must be equal to P on that side if you want them to run actually without any problems. You want them to run together basically. So when you are into US customary system of units, you use this quantity, and this actually tells you how close, it tells you the closeness of gears, the closeness of teeth, sorry. Okay, if this number is large, very large, you have more teeth for a particular diameter, okay? So in a small spacing, you will have more teeth. So and in other words, you can say that the teeth are very closer. So the teeth, so this diametrical pitch, you can think of it as a measure of proximity. You must have heard this name, a measure of proximity. Now this is in the US customary system. In SI system, you don't use this terminology. You just use its reciprocal. You see, it's 2R over N. So the numerator and denominator are swapped, and then you call it a module. So you will see both names, okay? In US customary system, you use diametral pitch, sorry, and in SI systems, you use module, yeah? So whether you use the module or diametral pitch, you just have a measure of proximity. Now, one more thing which is important, although I'm writing the name, but I'm not explaining all the detail. The way these teeth are designed by engineers, especially mechanical engineers, it makes sure to have some property which is very important. Yeah, because they are going to transmit motion from one side to another. So if you have spur gears, this principle is for spur gears, okay? And if you have this shape, if the teeth are designed according to this shape, okay? Don't go into detail. You should actually be more interested in what it means for you, okay? So involute profile is a way of designing teeth, and if you design the teeth in that way, you as a user will get this simplicity, and this is important now. If one gear turns at a constant speed, let's say this one turns at a constant speed, okay, omega 1, so will the other. The other will turn at exactly the same speed, okay, so omega 1 will be equal to omega 2. This means that this transmission will be without any serious problems. Now you don't want them to run at different speeds, because then they will not run smoothly. So fundamental property is the assumption. It is not stated in many books, but it is an assumption for the spur gears. This cannot be true for the other types of gears which we will study, but at least for spur gears, it's assumed, always assumed. Okay. So this also means that when these run at the same speed, there is no sliding. Yeah, no sliding. क्योंकि अगर ये different speeds से होंगी तो they can slide past each other. Sliding में you will have serious issues. Okay, you cannot rely gears if they are sliding. Okay, so that was spur gears. Okay, the next type you will see commonly is the rack and pinion. Okay, you remember pinion? What was pinion? I introduced pinion in the previous slide. It was the driver. Okay, so these are two gears. The pinion gear is the one which will drive the other one. So this will be connected to the load. This will be connected to the effort, and that's why you are calling it a pinion. But the load, the follower in this case is called a rack because it's straight. Okay, and you can see from the design that this can be used to convert rotation between rotation and translation. Okay, so you can for example, one possible application is steering front wheels. Okay, so the front wheels of a car are on the end and the engine produces power somewhere in the middle, so you definitely need a mechanism of transmitting this power. So you will see a need for converting between rotation and translation. And another application is positioning tables. You know, when you have in the milling industry, you typically have a cutter, and the cutter is stationary; it's not moving. So you need, and let's say there is a table, so you need to move that table so that it actually encounters the cutter, and for that you also need. So you will definitely need a pinion and rack mechanism. Yeah. Because typically you have motors, and the motors, they rotate, but you need to translate something, and this is a practical way of doing that. Okay, there are more complex gears. We will not get into all the details, but I'm just writing the names. I'm not even showing pictures, no pictures. So, but it's just important to know the names. So there are called, gears called bevel gears, and they are used to redirect connected shaft rotation by 90 degree. Okay, so if you have one shaft, let's say in this direction, and another shaft in this direction, and you want to connect these two, you need special types of gears. Okay, so gears must have teeth in a circle, and then they will have to have teeth in another circle at right angles. So you must have seen this. Okay, then there are helical gears. Now the problem with all these gears discussed so far is that these teeth, let's say if these are teeth on two sides, so because of this simple shape, they will engage with one another and then they will disengage. So the engagement when they encounter and the disengagement when they part, it is actually sudden. So they will suddenly collide and they will suddenly detach from one another. Now this produces many problems. This produces noise, and this actually produces stress. Yeah, sudden forces, impulses. If you remember, impulse is a sudden force applied over a short time. So If you want to make this smoother, you would like to change the shape so that they don't do this suddenly. They do that smoothly. So if you design the teeth in such a way that this engagement and disengagement is smooth rather than sudden, that is achieved by what is called the helical gears. Okay, the gears are not so simple; they are more complex, and they are called helical gears. If you want to understand this more, you can study it in detail. Okay, internet is full of all these pictures. So the advantage for you, what is important is that you should know what the purpose is to smooth out that, and as a result of this, you get less noise and less vibration. Yeah, undesirable, reduced contact stresses. Yeah, because when more area, basically this ensures more area. So when there is more area of contact, the stresses actually are reduced. Remember, stress is load per unit area. So if you increase the area, the stress will decrease. And they can also be used to redirect shaft rotation by 90 degrees, just like pinion and rack. But I mean, this is a different configuration, okay? So in that, this rotation, sorry, yeah, this bevel gear, this rotation is achieved by bevel gears when you have connected shafts, okay? So you have one shaft uh, and there is another shaft, yeah, and if you need this 90-degree rotation, if they are connected, you will need bevel gears. But if they are not connected, then you use helical gears. Now this detail, for this detail, you can actually read some literature. My purpose is only to give you these names, okay? And then there is the last type which we'll consider, that is the worm gear set. Worm gear set is a special case of helical gear, and it simply uses a design which gives you a large speed reduction ratio. For example, large because uh, you will see later on that the turn ratio, just like transformer, okay? So the turn ratio or the gear ratio, sorry, the teeth ratio to be precise, the teeth ratio, the number of teeth on one side divided by the number of teeth on other side. So if you have just one tooth actually going like like a spiral, and on the other side you have many teeth, so you get large ratios, okay? So so for us, we will see these names like bevel gears, helical gears, worm gears, and because we are not into detail, so each problem or example we are studying which uses these gears, enough details will be provided in the example, which means that you don't need to memorize all this detail even if you forget it, okay? Whatever is required in the example will be given to you um, as a comment. So we can now start some calculations on simple configurations, and that is the spur gears, okay? So we just study things for spur gears, and later on we can see, okay, how much of that can be applied to more complex gears. So if you see this now, you have two gears, or you can say a gear set. So this is the input side, and that's why you are calling it pinion, P. You also call this the driver if you want. And then you have an output gear. So remember, this will be connected to the effort source of effort. And the other gear will be connected to the load. And that's why you simply call it a gear. Or if you want, you can also call it a follower, okay? Now to understand the working of gears, it's good to have a free body diagram of each gear. Yeah. So the free body diagram for the pinion is this one. The free body diagram for the gear or the output gear is this one. Now look carefully at each free body diagram. If you look at this free body diagram now what are the external forces and torques? Yeah. So because this is a gear, the effort will introduce a torque. So let's call that torque TP. Yeah. Now, of course, this TP also means that there will be some force involved, okay? But when I write TP, torque applied to the pinion, it automatically implies a force. And of course, this will involve motion, so I write omega p for the angular velocity. Okay, because it's a free body diagram, this force or the force associated with this torque must be balanced by some other torque. But actually, because it's rotation, so you need a torque balance. You need a torque balance. Now we also need to introduce Newton's third law, because these are two bodies and these bodies interact. You know from Newton's third law that whenever two bodies interact, they will introduce a pair of forces. One will be action, the other will be reaction. Okay, because it is input, so this is the action. Yeah, this is the action, and this is the reaction of that. Okay, so this reaction will provide the opposing torque to this. So now in this free body diagram, there are two external things. One is the external torque and one is the external force from the other gear. So if we now apply the moment balance on this body, what will I write? Moment from this side is TP, yeah, and moment from this side, the opposing moment, is F times, let's say this is radius for the pinion, RP. Yeah? So radius for the pinion. So now this will be my torque balance. I'm just reproducing it. This is now the torque balance. Now this torque balance, why can we write that? Because you write balance, force balance or torque balance when something is at equilibrium, and we here assume constant speed. Okay, so if it's constant speed, it means there is no acceleration. When there is no acceleration, the torques must balance each other for each gear, and now I have done that for one gear, for the pinion. Okay, this is the external torque. This is also the external torque from the other side as a reaction. Okay, we can similarly write torque balance for the other gear, which is the follower or the gear. So here you see this arrow is understandable because it's just opposite to that. Yeah, and you can understand it in another way. This torque is clockwise, so the effect of this torque on this gear will be a downward force. Okay, that's obvious. Now because this gear has to be connected to a load, the load will be a separate body, and that load will oppose similarly action reaction pair. It will oppose because this F is producing a moment in this direction, yeah, anti-clockwise. So the load will present a torque which is clockwise, yeah, action reaction pair. Although action reaction pair is the word used for forces, but we are using the terminology of torques. So okay, we can write similar torque balance for the gear TG. Yeah, TG is the external torque from the load side, a reaction, and this F times RG is the torque from the driver side. So this is very easy. This you can write yourself, assuming constant speed. What else can we write down? You know that this motion is in a circle. So the pinion speed, yeah, the pinion speed, because it's a rigid body. So any point here, any point on the circle, yeah, this pitch, this what name did we use? Which circle it was? There was a name, pitch circle. Sorry, pitch circle. So you choose any point on this pitch circle, and the velocity, yeah, the tangential velocity can be called VP, P for pinion. Okay, and you know for translational velocity in a circle, it's simply related to radius times the angular velocity. Okay, you can do the same for gear speed. You write the same equation for the gear, and because there is no sliding, remember that fundamental principle where if there is constant angular speed, it will be the same for both, so that there is no sliding involved. That requires, no sliding requires, actually no sliding corresponds to the velocities where these two parts contact each other. Okay, so if this side moves, let's say, downward, then this side will also move downward. Okay, and they must move at the same speed if you want no sliding. That means that these two speeds must be equal. Yeah, and when you, okay, one more thing, we also require diametral pitch to be the same for both. So the number of teeth per unit diameter must be the same for both. Okay, so I'm just writing this equation. It's just a repetition of the previous slide. Now, if I combine these different relationships, yeah, the fact that the two velocities must be the same, the two speeds, and the two pitches must be the same. So you can now connect the angular velocity of the output to the angular velocity of the input. Yeah, we just equate these two. For example, if I plug these expressions here, what do I get? I'll get rp times omega p, that should equal rg times omega g. I solve this and I'll get an expression for omega g in terms of omega p. And because of this requirement, it turns out that the ratio of the radii can be written as a ratio of teeth. Yeah, and you can easily count teeth. No, measuring radius is not easy, but counting teeth is so easy. So which means that the angular speeds are simply related by the teeth ratio. So we will just call it the teeth ratio. It's just like transformer. And this equation automatically gives us velocity ratio or movement ratio. The ratio of speeds, that turns out to be the ratio of teeth. So we discussed this already. You can also write, these equations can be combined to write a transformation for the torque. The torque at the output can be connected to the torque at the input, first through a ratio of diameters and then through a ratio of teeth. So what you need to remember, I mean, of course, this derivation you can do at home as well, but what I want you to notice is something very interesting. The velocity ratio is np over ng, the number of teeth for the pinion divided by the number of teeth for the gear. But that same ratio for torque ratio is the opposite. It's ng over np. So which means that if you want the efficiency, remember the efficiency is simply the force ratio divided by the moment ratio. Now force ratio will be related to torque ratio, so you expect an efficiency of 1 if we are ignoring losses. Okay, and you can establish this thing indirectly as well. Okay, because here we are not using force ratio, we have torque ratio. So let's say Pg, power at the output, is simply torque times angular speed, Tg omega g. And because of this torque ratio, or because of this transformation, you can plug the value of Tg in terms of Tp, and that, if you cancel out all these teeth ratios, you will see that, okay, Tg omega g is the same as Tp omega p, and that is actually the power for the pinion. So the input power, this is the input power, and this is the output power. So when the input power and the output power are equal, that simply reinforces the efficiency, the mechanical efficiency is 1. Of course, we are only here focusing on the principle, and we are not considering losses or any thermal losses or friction losses, things like that. The take home from this slide is if I want to encircle this relationship, yeah, and when you know this thing, this comes automatically because this is just a real formulation, and this relationship, yeah, and you can memorize it that for the angular speed, the ratio is actually the teeth ratio for the pinion to the gear, but for the torque, the ratio used is for the gear to pinion, so it's just the opposite. Okay. Now we can attack some problems. So let's say we have, it's a very simple problem to start with. Let's say we have a driver gear, which means a pinion. Okay, I can just write pinion here. Pinion. On a shaft of motor has 35 teeth. So I can think of this as NP, yeah, number of teeth on the pinion. And it meshes mean that it actually combines with the follower. Follower is your gear, okay? So this teeth is NG. So NG is 98, and NP is 35, okay? If the speed of the motor is 1400 revolutions per minute, okay? So the speed of the motor, omega. Now motor is connected to the pinion, so that will be omega P, okay? Speed of the motor is the same as speed of the pinion because motor is connected to the driver or pinion. So this is simply 1400 RPM. Now by proper conversion, you can turn this into radian per second, okay? That's important. So when you turn this into radian per second, now you want to know, find the speed of rotation of the follower. You just want to know omega G, okay? Speed of the gear or the follower. So we saw that there was a transformation where you can go from the angular speed of the pinion to the angular speed of the output gear, and this ratio was NP over NG. Okay, you simply plug these two values and you get your answer. So easy. So difficult is to spot from the statement which one is the gear, which one is the pinion, and the formula table will be given to you anyway. So okay, now, so one thing is very clear that just like you have to connect many batteries, okay, if you need a large voltage, the batteries available in the market may not be enough, so you have to connect batteries, or similarly resistances, okay, resistances in series, batteries in series. So the same is true for gears. Remember, each gear set ultimately gives you a transformation, a ratio of speeds and a ratio of torques. Now, I mean, one thing which you can understand from these two is that because TR is 1 over VR, okay, it's the reciprocal. So you can only increase one of these two because power does not change. So you can either increase the torque ratio between these two gears. If you increase the torque ratio, the velocity ratio has to decrease. Or if you want to increase the velocity ratio, the denominator has to increase and then the numerator has to decrease. So which means that gears, they do allow transmission of motion, but they can only amplify one of these two variables. जिस तरह ट्रांसफार्मर में होता है ना, प्राइमरी और सेकेंडरी में वोल्टेज और करंट दोनों को आप एम्पलीफाई नहीं कर सकते, आप एक को एम्पलीफाई करेंगे दूसरे को कम करना पड़ेगा. ठीक है. Now, so when one gear set is not enough, you combine gears, okay? So here you see 4 gears now. This is the driver, and that's why we are just calling it the input. This is the follower, the output, and there are 2 gears in the middle. So let's use N1 for the number of teeth of this one, N2 for this one, N3 for this one, and 4 for this one. So you just label the number of teeth like that, 1, 2, 3 from the drive. So the labeling starts from the input side and it ends at the output side. and then you have the angular speeds, yeah, omega 1, omega 2, omega 3, omega 4. Okay, so if you assume that the input torque is clockwise, this is just an assumption, you can change the assumption. So the first angular velocity, angular speed has to be accordingly. It has to follow that, okay? Now, remember, because this has to come down and because there must be no sliding here, so this side must also come down, which means that this angular speed has to be opposite. These must be opposite, yeah, because they must be running together. You don't want them to fight each other. So similarly, these two are now opposite. So if this is going upward, this also has to go upward, which means that this has to be clockwise. And again, these two, this has to come downward, this has to come downward. These angular speed are opposite. So it's very easy. Now, so I expect you to know this sense. Okay, you should be able to have to indicate proper directions. Okay, now we use results from the previous slide to have an expression between omega 1 and omega 2. Yeah, relationship between these two is the teeth ratio. So this teeth ratio is involved there. Okay, that's a good thing. Now we can do the same for the angular, the speed, the relationship between omega 2 and omega 3. So I take this as my output and this as my input, and I use similar relationships. Yeah, and because omega 2 is available from the first equation, I can plug it, and after some cancellation, I will get a direct relationship between omega 1 and omega 3. So you can simply ignore this. Okay, so omega 1 can be connected to omega 3. Yeah, and it's connected in the same way, you see, n1 omega 1 and 3 omega 3 and 1 omega 1 and 2. So this intermediate gear actually can be called as an idler gear because it doesn't affect the relationship between the input and output. So that's why it's called the idler gear. Gear 2 is an idler gear. You can do similar stuff between 3 and 4, follow the results from previous slides, plug these two results, and it turns out that the relationship between omega 1 and omega 2 is also of the same form. Yeah, n1 divided by n4, which means that gear 3 is also not influencing the overall calculation. It's just helping it. So both 2 and 3 are called the idler gears. And now why is this so? And why are we calling it simple gear train? Because you remember these parts which you see in the diagram, they represent the shafts. Okay, so there is one shaft and there is one gear, one shaft, one gear, one shaft. So if each shaft maps to a single gear, one gear per shaft, then you have a simple gear train. That's why these relationships are so simple. Okay, because between two gears there is only one point of meshing. So there is meshing between 1 and 2, there is meshing between 2 and 3, there is meshing between 3 and 4. There is no double meshing or triple meshing. That's why these relationships are simple. If you want, you can turn that result into ratios for velocity and torque. So velocity ratio is this one, torque ratio is this one, and you see even for the gear train or a sequence of gears, these two are reciprocals, yeah? And 1 over 4 and 4 over 1, which means that the efficiency we assume is has to be 1. Okay, although remember this is misleading because efficiency is not equal to TR over VR. Okay, it is equal to FR over VR. But of course, FR will be connected in a simple way to TR. Okay, so we can do that later on. So I mean, you can combine these two by showing that the output power is equal to the input power. You can show that as in the previous slide. Now, sometimes this simple gear train is not enough, and you need to have, now in this case, you don't see any difference in this view, but if you look, if you see the top view, of course, here you have one shaft and one gear. Yeah, this is the shaft, and this is the top view of the gear. Here is also one shaft, one gear. So the input and output are very similar to what we had before, but in between, instead of two gears side by side, we have both these two gears mounted on the same shaft. You see? So this gear and this gear, they are both mounted on the same shaft. This is the smaller gear, this is the larger gear, and they are both on the same shaft. So which means that this is a single meshing. This is also a single meshing, but here you have two meshing, yeah, mesh points. Now the consequence of that, what is the consequence of that? If you want to write the transformations, the transformation between omega 1 and omega 2 doesn't change, it's just like before. But the transformation between omega 2 and omega 3 is special. They must be equal. There is no ratio involved. Why? Although these are ratios, this ratio, these teeth are more than these teeth, but because they are on the same shaft, when we were calculating these ratios worked because there were different shafts. When there were different shafts, this meshing forced that ratio. Now they are on top of each other. So both these gears must be moving at the same speed, the same speed. Now, when you combine these two for the third equation, you don't get a simple relationship. Now you have to multiply the two ratios. N3 over N4 and 1 over T, N2 there is no cancellation. Okay, and this is how you get more amplification. Okay, you can get larger ratios in this way because of no cancellation. So in this case, you can see that these two gears, they do have a role in the overall relationship from omega 1 to omega 4. This is the input, this is the output. This gear does have an impact on the relationship. You see, इसका जो अपना N2 है वो भी इसमें आ गया और जो N3 है वो भी आ गया. दोनों N2 और N1 का रोल है फाइनल कैलकुलेशन में. यहाँ पे वो रोल नहीं था. फाइनल इक्वेशन में N2 disappeared and N3 also disappeared. Yeah. In the final calculation, you only see N1 and N4. That's why we call them idler gears. In this slide, there is no idle gear. No, all the gears have a role to play. Okay, and of course, these relationships can also be converted to velocity ratio and torque ratio. Even there, although you see some complication, but velocity ratio and torque ratio, they are reciprocals of each other. So it's very easy, which simply means that if you combine these two, you can show that P input is equal to P output. Yeah. Okay. The next slide is an example, and you have simple gear train. Okay, simple gear train, which means that one shaft, one gear, one shaft, one gear. This is your input side, which drives the gear at 250 RPM. The teeth are 80 for the pinion, 30 for the idler, and 50 for the output gear. And omega output is for the angular speed of the output. Remember, let's check this ratio. Okay, let's check this arrow. So if this motion is clockwise, because of this meshing, common meshing, this has to be anti-clockwise because they both must be moving together. And this V omega out must be opposite of this. So this arrow is correct. Okay, the arrow is correct. Now the motor power is 1 kilowatt. Okay, which means that we are given PG, G for the gear. No, sorry, G for not G. Sorry, PP, P for the pinion. PP is 1 kilowatt. You can also write it as 1000 watt if you want. RPM, so omega P is also given, which is 250 RPM, and you are supposed to convert it into radian per second. Okay. Now determine the speed in part A, determine the speed and rotation direction. Rotation direction तो हमने कर दिया ना already. We only need to find the speed of the output shaft. Okay. So direction हमने already सही शो किया हुआ है. Speed के लिए क्या है कि you just need to write the formula. Because this is a simple gear train, so the omega out divided by omega n, which is omega, yeah, this will be the teeth ratio. Actually, we don't need to write it in this way. We just write the transformation. So omega out is equal to omega n, which is omega p, and the ratio here is that this number of teeth must match p, so it is np, and this one must match that. This is only true for angular speeds, okay? For torques, it's the opposite. So it's n out, yeah. N out, remember, is 50. N out is 50. So you just plug these values and you get your omega out. Now, what magnitude of torque? Now, this is part A, okay? In part B, you are asked, what magnitude of the torque does output shaft transfer to its mechanical load? So you need to calculate torque load, yeah? Torque load, or torque output, sorry. Torque output. Now, because we assume that there are no losses, we can simply say that the input power is equal to the output power. Yeah, input power we know is 1 kilowatt. So we simply say 1 kilowatt. And output power we know is the torque times the angular speed. Yeah, so angular speed will be omega out and it will be T out. Now, so if we know this thing, which is 1 kilowatt, and we have calculated omega out in the previous part, this equation can be solved to work out T out. See, so there's no rocket science. You just need to remember those relationships. Okay. The next one is a bit complicated, but you should not be scared actually, because the detail is given here. So this seems to be a compound train, yeah, a compound train. It's not a simple train because no, it's also a simple one. You know, one shaft, one gear, one shaft, one gear. Okay. No, sorry. On this shaft you have two gears. On this shaft you have two gears, so it's not a simple mechanism. So a gear reduction mechanism is used in a machine that accepts bill currency, inspects it, and returns a coin and change. So जिस तरह उसको जो है ना notes को देख रहा है. The number of teeth on the pinion and gear in the first speed reduction stage are shown in the figure. तो pinion के gears यहाँ पे कितने हैं? 10 है. So you can say NP is 10 and NG is 23. अब इसके बाद क्या है? The worm, ये worm gear है, ठीक है? ये वाला वो complex shape जो है has a single tooth. देखो ना इसका, देखो ना ये अगर आप इधर देखिए एक ही teeth जो है ना helical की तरफ जा रहा है. So it's a single teeth, a tooth that meshes with 16 tooth worm gear. देखो ना ये जो इस worm gear के 16 teeth यहाँ पे सिर्फ 1 teeth के साथ है. So यहाँ पे रेशो जो है ना आपके पास 1 to 16 रेशो मिल जाएगा यहाँ पे, ठीक है? It can change the ratio from 1 to 16. Determine the velocity ratio between the output shaft speed and the speed of the direct current motor. So हमें क्या required है? Output shaft speed omega out and we need to find out the ratio between omega out and direct current motor, ये इसका जो स्पीड है, which is omega n. ये इनपुट स्पीड है, ये आउटपुट स्पीड है. We need to calculate this. Okay. Now this shaft in the middle, this transfer shaft is common, okay, because this same shaft is involved here and this same shaft is involved here, which means that if we want to write the transformation for these two gears in this meshing, this is the meshing point. This is the meshing point. So for this meshing point, I have two gears, this one and this one, the pinion and the gear. So I can write the transformation ratio as इसका जो output है वो omega ट्रांसफर शाफ्ट है, लेट्स कॉल इट ओमेगा ट्रांसफर, या इसका जो ट्रांसफर शाफ्ट का है ओमेगा ट्रांसफर, इस मेश पे आउटपुट है और इस मेश का जो इनपुट है वो ओमेगा एन है, ओमेगा एन फ्रॉम द मोटर साइड. ओके, ओमेगा एन फ्रॉम दी, बिटवीन दीज टू आई कैन हैव ए रेशो. इस साइड पे रेशो जो है ना वो है 10 और इस साइड पे रेशो 23. सो 10 divided by 23. Now I can apply the same for this meshing point. इस meshing point पे मेरे पास ओमेगा आउट है, ठीक है, ये ओमेगा आउट है और ये आपका ओमेगा ट्रांसफर है, ठीक है. So between these two you can write the ratio. ओमेगा ट्रांसफर शाफ्ट वाला जो साइड है वहां पे there is one tooth और जो आउटसाइड वाला है वो क्या है, वहां पे 16 है. Okay. So you can now combine these two, you can eliminate omega transfer because वो इसमें भी आ रहा है, इसमें भी आ रहा है, and that will give you, I can simply write just like chain rule कि omega out divided by omega transfer divided by omega n, और ये दोनों basically इधर से आ रहे हैं. Yeah. Each of these equations will give you one ratio and you just actually apply that. So look, इसमें जो take home lesson है कि this example uses a name which you have not heard, the worm gear, but enough information is given to you. आपके लिए इसका सिर्फ ये जानना जरूरी है कि यहाँ पे 1 tooth है और यहाँ पे 16 है, तो ये रेशो 1 to 16 आप फिर भी लिख सकते हैं. बाकी इक्वेशंस शायद आप ना लिख सके, लेकिन मतलब you don't need to get scared when you see a new name in a question because enough information will be given to you to utilize that. Okay. So अब यहाँ पे अगर मैं if I remove all the annotations, the punchline for this new name is this: the worm has a single tooth that meshes with 16 tooth worm gear. Now if you understand this, this leads to that ratio of 1 to 16, and that solves your problem because that ratio allows you to relate the speed of the shaft, the transfer shaft, to the speed, to the output speed basically. ये output speed था ना आपका. So I think this was mostly the examples from that chapter. We can, हमारे पास अभी टाइम कितना बचा है अभी? Let me just check. 40. So we have 5 minutes, and in those 5 minutes I can only try one more question, which is very simple. Okay, this will require you to switch the context because this question doesn't seem to be a question of lever or gears. ये gear और lever का question नहीं है, ये लेकिन आपको जगा देगा, ठीक है. So you just have an automobile, you have to figure out कि कहाँ से आया है question, किस topic से है. You have an automobile that travels at 30 miles per hour. तो एक speed given है आपका, ठीक है, 30 miles per hour. And because this must rotate, तो ये center का इस point C का speed, you can think of it as if this अगर आप इस रोटेशन को ना भी देखें तो एज ए होल ये ट्रांसलेशन भी है और रोटेशन भी है, ठीक है ना। एंड बिकॉज देयर इज नो स्लाइडिंग इन्वॉल्व्ड, सो दिस 30 मीटर पर आवर जो इसका स्पीड है, लेट्स कॉल दिस v, ठीक है, v इक्वल्स 30 मीटर। तो आप मुझे बता सकते हैं कि ये कितना होगा, इस पॉइंट का स्पीड कितना होगा? ये तो आगे जाएगा, पीछे तो नहीं जाएगा। कोई बता सकता है कि वो कितना होगा? इफ आई कॉल दिस v, सो ये कितना होगा? और इस पॉइंट पे रिमेंबर दिस साइड हैज टू मूव बैकवर्ड अर्थ के साथ, ठीक है ना, क्योंकि रोटेशन का मतलब यही है कि इट विल बी लाइक दैट। सो ये कितना होगा, ये कितना होगा? स्लाइडिंग ना होने का मतलब ये है कि अर्थ के साथ चूंकि स्टेशनरी है तो ये जीरो है, ठीक है। ये जीरो क्यों है मुझे बताएं, ये वाला? क्योंकि यहां पे ये स्किडिंग स्लाइडिंग अलाउड नहीं है, ठीक है। So it means that there is a relative motion between these two. Okay. You can say that this point moves at this speed with respect to the Earth, but you can flip this argument. You can think of this as stationary and you can imagine as if the Earth is moving. तो आपको अगर ये अर्थ मूव होती हुई नजर आ रही है, वो रिलेटिव स्पीड है, ठीक है, एब्सोल्यूट स्पीड नहीं है। तो आप चाहें तो आप इसको जीरो कह दें और ये फिर हो जाएगा -30 miles per hour, ठीक है, इफ यू वांट इट दैट वे। But चूंकि we have already labeled it, so this will be zero, and this will be, remember, ये motion without sliding तभी हो सकता है जब इसका twice हो, so it has to be twice 30 meter per hour, miles per hour. Okay, this is something which you must have studied in physics courses. Radius आपको given है 15 inch, yeah. So you just need to know the rotational speed of the tire in units of radian per second, degree per second, RPS, RPM. ये तो conversions है, but formula आपको पता है कि V equals ओमेगा R। ये V इस टाइम पे आप चाहें, अगर आप ये वाला V लेते हैं तो आपको रेडियस ये करना पड़ेगा। अब अगर आप ये V लेते हैं, ठीक है ना, तो ये V इसलिए ले सकते हैं कि ये रिलेटिव मोशन है, ठीक है, ये रिलेटिव मोशन है। इन दो के दरमियान जो रिलेटिव वेलोसिटी है वो इन दोनों का डिफरेंस है, तो इट विल नॉट बी 2v इक्वल्स, इट विल स्टिल बी v इक्वल्स। तो यहाँ पे आपके पास, इफ यू वांट टू सॉल्व दिस, यू हैव ओमेगा इक्वल्स v ओवर r। v आपको गिवन है 30 miles per hour and you multiply this so that you get proper units in meters per second, and here you have meter per second or foot per second, and this 5 inches must be multiplied so that you get proper units. So ये that was easy, okay. बाकी क्वेश्चन हम नेक्स्ट टाइम कर लेंगे इंशाल्लाह। Make sure that you write P. And I'm stopping the recording.